Right. The intent of this video is to show how you can use some tools in Excel to do hypothesis testing, both for means and also for proportions. Now, I will say that Excel is much more built around being able to calculate, do the hypothesis testing for means rather than for proportions. So we're going to have to do some templates to get the proportions to work. But before we do that, for the means, there are some built-in tools, but to get to them, you will need to activate the data analysis option, right? So in order to do that, hop into Excel, you go into File, right? Under Options, and in here you need add-ins, Manage Excel add-ins, go. You'll need to make sure you've checked the analysis tool pack and click OK. If you do that, then you will have under your data tab in the ribbon, you'll have data analysis appear off to the right. So that is something you're going to need for some of these tools we're going to be using. All right, so with no further ado, I'm going to go ahead and zoom into Excel and we'll focus on the task at hand. All right, so first task. Let's get a hypothesis test for means. We're testing for a single sample, the mean versus a hypothesized value. So that's our goal here. So what I have here is a selection of, it looks like 25 months of data of unemployment rates for the Canton, Ohio area. Right, so what I'm going to test is the hypothesis that the mean unemployment rate in Canton is 5%. And now since I'm using a sample here, that means I can't just calculate the average and see whether it's 5% or not. Instead, I have to use hypothesis testing types of techniques. Now, the way that things are built in Excel, it's really designed to test one sample against another sample. Here I only have one sample. So I'm going to create a second sample, an artificial one, which I'm just going to call hypothesized here. So I'm just going to add in column B, hypothesized, there we go. And it's only going to contain two values. Those two values will be identical and will be the same as the value that I'm testing against. So in this case, I want to know, is the mean unemployment rate in Canton equal to 5%? So 5% is what I'm looking for here. In this case, they're all stated just as integers instead. That's fine. Just put in the 5. We're good to go. All right, so we've got 5 and 5. Now let's do it. So we need to go into our data analysis tool. And it gives us all kinds of options. The option we want this time is under these t-tests. These are 3 different types of hypothesis tests we can do. We want to focus on this last one, 2 sample assuming unequal variances. In our case, we constructed it so that the second sample has literally 0 variance. That is, we have 2 values that are exactly the same as each other. Clearly, our actual data is not going to all be exactly the same. So unequal variances would be true. So we'll click OK here, and then this is the input that it wants. It wants to know what's my variable 1, my variable 2, do we have a hypothesized mean difference, am I including labels, I need my alpha, which is the level of significance, and then where am I going to put the output? So let's go ahead and do that. So first variable, that's going to be my actual sample. So here it's here in column A, so I'm going to highlight that like so, and that's good. Second variable, that's the hypothesized one that I have here. Hypothesized mean difference, actually it's going to be 0. I want to know, is that equal to 5? So I'll just leave that blank. If you leave it blank, it assumes that it's 0. I did include labels. That is, I include the headers for those 2 columns. So I'm going to click check mark for labels. Alpha, my level of significance of 0.05, that's fine with me. I do want to put the output here in the same spreadsheet like I did just there, right? So it's going to create an output table starting in D1 and then moving to the right and down from there. And then I'll click OK. And there we are. Right, so what it has done, it is now created for us this table, right, where it's giving us, okay, I need to widen that a little more. Okay, some information about both of our samples. So what is the mean, right, what is the variance, and then also how many observations are there in each sample. And then it has all the information for our test. I need to go down one more row. There it is. So that's all the information for the test itself. Okay. So how do we use this? Right, so the first thing we need, right, first just at a glance, 5.544 and 5 are not the same. They're not exactly equal to each other, but the question is that difference enough, right, to say that, you know, it is statistically significantly different. It's not just not quite exactly the same. Right? So in order to show that, we need to know what our t-statistic is here. So that is looking at the difference between the two and then dividing it by the standard error. That gives us roughly 3 is the answer there. And then we can compare that t-statistic with the appropriate critical value. In our case, because we're testing for equality, we would use the two-tail information. Right, so our t-statistic of 3 or so is outside of the t-critical of roughly 2. So that would suggest that these are in fact sufficiently different from each other that it is a statistically significant difference. Another way we can know that is by comparing our alpha that we chose of 0.05 with the p-value reported here. Again, for the two-tailed test, because we're doing equality. So the way that I think of p-value is that the p-value that is calculated tells you how consistent is the data with your hypothesis. The higher the number is, the more consistent the data is with the hypothesis. Right? So what that 0.05 that we chose does is it's really saying, you know what, we're okay as long as it's at least that level of consistency, that p.05, as long as we at least hit that, then the data is close enough to the hypothesis, the null hypothesis, that will just act like it's true. Right? On the other hand, what's happening here is that our p-value is less than that 0.05. That tells us the level of consistency of the data with our hypothesis is lower than we can tolerate, which then would lead us to reject the null hypothesis. We're not going to act like it's true. We're not going to act like this is actually a 5% unemployment rate, because it's not. They're statistically different from each other. Now, are they practically different? Well, that's another question, because what we found here is that in our sample, okay, it's not 5%, it's about 5.5%. Is that going to lead us to have radically different policies? Maybe, maybe not, right? But the matter of practical difference and statistical difference are things we kind of have to think about. So statistical difference is very clear to establish. That's just compare the t-critical versus your t-statistic, or compare your p-value versus the level of significance. That's a cut and dry, yes, statistically significantly different or not, based on the p-value that we chose, or based on the level of significance we chose. The practical difference is one that is a little bit murkier, and that's really just a matter of the specific case that you're dealing with. Okay, so this is how we do hypothesis testing for means if we have a single sample. Okay. Now let's look at what if we have a single sample and we're doing hypothesis testing for proportions. Now, unfortunately, Excel is not well designed to deal with this directly. So we're going to have to, say, finagle it a little bit. Right? So we're going to create a template that is going to do this for us. And there's our blank sheet that we're going to use for our template. And now let's go ahead and start putting things in. So first, we're going to have 4 different inputs that we need to put. Right? So one is the number of successes that we have in our sample. Next would be our sample size. Then we need our hypothesized proportion. That is, what do we think that that proportion is going to be. Then our alpha, which is our level of significance that we've chosen. Right. Then we're going to calculate a few other things after that, but let's handle that first. Okay. Right. And I want to widen that. Right. So remember, the successes, that'd be how many observations in your sample have the trait you're looking for. Sample size, just how many total observations are there in your data. That hypothesized proportion would be, what is your comparison point? Right? What is it you're comparing to? Right? And then finally, alpha, the level of significance you've chosen. Right? What is that cutoff for the p-value that you think would be acceptable? All right, now our calculations. Right? So the first one is going to be p prime. So p prime, that would be your sample proportion. To calculate that, you need the number of successes in your sample. Divide that by your sample size. So that would give you what percentage of your sample is made up of successes. In this case, it's dividing by 0 because I haven't put any input in yet. Okay. Then we need to calculate the z-statistic. The z-statistic is going to compare, right, what is the level of our actual sample data, what does that have for its proportion, subtract off the hypothesized proportion. We start with that. So what is the difference between the two? But then we need to adjust this in terms of the standard error. So we need to divide by the standard error we calculate as square root of that hypothesized proportion times 1 minus the hypothesized proportion. And then we take that thing and we divide it by our sample size, and then finish that out. Right, so it takes the square root of that whole thing. And that's how we calculate standard errors. We use this as well for things like calculating confidence intervals. It's the same basic formula. All right, so that would be our z-statistic. We hit enter. Again, division by 0 because we haven't put in any data. Okay. The last thing we need then is the z-critical. We need 4 things: our z-critical if it's one-tailed, z-critical if it's two-tailed, p-value if it's one-tailed, and p-value if it's two-tailed. So I'll do the one-tailed stuff first. So z-critical. The formula for that, we use the absolute value that is going to turn whatever number we have in here positive. Then we pull from the normal distribution, but we have to invert it. What that means is that we give it a probability, and it will tell us where along our x-axis we have to go to get that much probability to the left of it. Right? So in our case, the probability we want, right, is going to be our alpha. There we go. And then we mean of 0, standard deviation of 1, because we're dealing with a standard normal. And standard normal, by definition, is mean 0, standard deviation 1. All right, so that's good. Enter there. Then we need the p-value for one-tailed test. Here, again, we're going to be pulling from the normal distribution. But now what we're going to do is take a look at the actual value we have for our z-statistic. So we select that. And then we would apply to, oh wait, so we're not going to take that directly actually. We want to make some adjustments to it to make sure we get exactly the value we want. That is, we're going to take the negative absolute value of it. Right, so it's going to take whatever our z-statistic is, right, turn it positive, and then turn it negative. This is just to ensure that we're feeding a negative number into the normal distribution, because that is then going to give us the p-value that we want. Okay, right, so otherwise we could end up with something like 0.99 instead of 0.01. Is the problem. So we want to make sure we're looking at the left side of the distribution where our x's will be negative. Okay. Our mean is 0, our standard deviation is 1, because again it's the standard normal. Cumulative, yes, this is true. So it's looking at the area underneath the normal distribution to calculate that p-value. All right, and then enter. Again, division by 0 because we don't have data in yet. Last 2 bits. We need the z-critical, but not for one tail, instead for two tail. All right, and absolute value of normal.inv. So it's the same kind of formula as before, but now because we have 2 tails, right? So remember that alpha is capturing kind of the level of significance is basically, the way that I think of it is how much weight are we allowing, right, in the tails. Right. Now, if we only have one tail, then all the weight would be concentrated in one tail. If we're allowing, though, that 0.05 weight, but we're dividing it between 2 tails, then we have to divide it up. So it'd be 0.025, right, in either tail. So that's what we need to do first. The probability here, we take that tail, right, that alpha, and we divide it by 2, because we have 2 tails it's divided between. And then again, 0 and 1. Okay. The last, oh, I made an error there. Oh, I forgot one of my, you need to make sure you have 2 parentheses there, because we have to close both the normal invert formula as well as the absolute value formula. Okay. Oh, let's close this there. Yeah, that gives us more space. Okay, cool. And then p-value for two-tail. This one is actually really an easy calculation. Since we already have it for one tail, we can just take that and multiply it by 2. There we go. So 2 times b10 would get that for us. So let's show this in action. Let's say that we have a coin, and I want to know whether this is a fair coin or not. I think it probably is. That's my hypothesis. My hypothesis is that the proportion of times that I flip that coin that it comes up heads is going to be 50%, so 0.5 here. As our hypothesized proportion. Professor, there it is. Okay. And let's say that I think that a perfectly appropriate alpha would be 0.05. That's typical, and let's say I'm comfortable with that. Okay. All right. Now I take that coin. I flip it 300 times, so we have a 300 sample size. And of that 300 times, it comes up heads 160 of them. Now our formula is all filled in. So we have all of our input. Number of successes was 160. 160 of them were heads. 300 coin flips. 0.5, that is, we think they're going to show up about half the time as being heads. And then the level of significance we chose is the standard one of 0.05. Okay. Putting this all together, we end up with a p prime. That would be our sample proportion is 0.533 repeating, so basically 53%. Z-statistic of 1.13. 0.5 or so. Right? So is that 0.53, is that close enough to 0.5 or not? Well, that's where we compare. In this case, it's again a two-tailed test because we're looking for equality. We want to know, is that equal to 50%? So two-tailed test. I like the p-value. So I compare the p-value, roughly 0.25, with my alpha of 0.05. Remember, 0.05 is the cutoff of the level of consistency we need to say our null hypothesis is at least true enough, we can't reject it. And it looks like we have that. In fact, our level of consistency, the p-value, is 0.25, so it's well above 0.05. So in this case, it looks like there is no statistical difference between a fair coin and the coin that I actually have and flipped. So that'd be proportions with a single sample and what the template would look like, how it works. Now let's look at a hypothesis test with means, but where we have two samples. And that's really what Excel's tools are designed to deal with. Right, so in this case, we have two different groups. In this case, I'm looking at students. One group did all of the homework in the class and then took an exam. The other group did not do all the homework in the class and then took the exam. Now, it might be that they only missed one. It might be that they missed three. It might be they missed all the homework. But in any case, that is how we have things divided up. Those who have the perfect homework record and those that don't have a perfect homework record. So, I want to know, do they earn different test scores or not? Do they have different averages on their tests? Right, so my null hypothesis is that they will be the same. Right? That is, that it won't actually make any difference. Right? The alternative being that it will actually make a difference. One of the means is going to be different from the other. All right, so in that case, we have to decide what type of test we're going to do. And what I mean by that, let's open data analysis and I'll show you. So we have these three different tests. Paired two-sample for means, two-sample assuming equal variances, and two-sample assuming unequal variances. So what each of these is. For paired two-sample for means, this is sometimes called matched pairs. In this case, you have these two samples, and you have some way that you can match up each observation in one with one observation in the other. This is most common if you're doing like a before and after kind of scenario. So say I'm providing training. So I have people take a pre-test, they do the training, then they take a post-test. Then what I can do, I can pair the pre-test score with the post-test score for the same person. So that same personness creates a connection between the two. Now sometimes you can do this artificially. Say that you have, say, two different sets of cities that you're running ads in, and you have each set of cities so that each of them has basically a sister city that is very similar demographically. Right? So in that case, it's not exactly before and after, but you at least have some way that you can pair each member of one sample with each member of the other sample. In this case, we can't do that for a simple reason. There are different numbers of observations. Way fewer people did all the homework than didn't do all the homework. If you don't have the same sample sizes, you can't possibly pair them together. Right? So that leaves the other two. Right? So assuming equal variances versus assuming unequal variances, I think it's fairly clear what that means. Assuming equal variances, that is, we think the spread of the data is going to be basically the same in both of the groups. Assuming unequal variances would be if we don't think the spread will be the same. Now, of course, we can't always just calculate the variance to see if it's close. But in my case, I'm going to just work with the assumptions of what's going on here. I think if everybody does the homework in a particular group, their scores on the test are going to be similar because they have a more similar background. Whereas the people that did not do all the homework, there are lots of reasons that might have happened. It might be that somebody's very busy, so they didn't have time to do all the homework, they didn't have much time to study, so they didn't do the homework, and they're also not going to do well in the test. But somebody else might have decided not to do the homework because they already know the material. Like maybe they took the course before, had a different version of this course or something like that, and just had to take this particular class, so they're just not doing the homework because they already know the material. In that case, they could score very high, right, even though they didn't do all the homework, or perhaps didn't do any of it. Right, so I think assuming unequal variance is what I'm going to go with, and I would say if you're not sure, you can always run both and compare to see if it makes any difference. Also, the test will actually calculate the variance for you. So if you run one of them, and then you see the variances actually look very different from each other, you can always run it again, or if they look very similar to each other, you can always run it again. Right. All right, so let's go ahead and check this. I would say if you're going to default to one, because you're not sure, default to unequal variances. And then I'm going to go ahead and click OK. All right, so I need, again, my variable ranges. So for variable 1, I select the A data. So this is for those that did all the homework. Then those that did not do the homework will be my variable 2. And scroll down. There we go. Hypothesized mean difference, again, is going to be 0, so I leave that blank. I did include labels and 0.05, yes. Output range in D4. Yeah, that looks good to me. So click OK. And here's what it gives me for output. All right, so we have the mean for those that did all the homework, roughly 64. Those that did not do all the homework, roughly 54. So at a glance, this feels like it's a difference. Meanwhile, the variances, you can see here, we're not quite as different as I might have guessed. Right? It probably would have been okay looking at these two to just assume equal variances because they're not radically different from each other. But either way, I ran the test that I ran. All right, so let's look. Number of observations in each of our samples is also reported. And then the DF, this would be the degrees of freedom. Now that one, the calculation for this particular test gets complicated, right? So don't worry too much about that. Instead, we're going to focus on the results here. Right, so our t-statistic was basically 3.34. Right, now in this case, it's a two-tailed test because we're just looking for a difference. Right, so our p-value here of 0.002, if I round, is definitely less than 0.05. So I would reject my null hypothesis that there is no difference and say, actually, there is. It does look like those that did all the homework did have different test scores than those that did not do all the homework. Now technically, that is what the hypothesis test tells us because I was just testing for equality versus inequality. However, it's also true that if you do a two-tailed test and you find that there is a difference, you can also say which direction that went. So in this case, it is in fact statistically valid to do that. So in this case, I can say not only that there is a difference, but that in fact those that did all the homework scored significantly higher in the statistical sense. Now, whether it's a practical difference, these 10 points, well, that's again a matter of judgment as far as that goes. Okay. Although I think in an education context, 10 points is often a letter grade, so that feels significant as far as that goes. All right, so now the last one. So we're going to look at a hypothesis test for proportions with two samples. Right, so what we have here is one example of that. This is A/B testing, which is a way that they test marketing. Right, so this would be something you might use for, say, banner ads or Facebook ads, that kind of thing, where you have two different ads that you show, and they each go to a different set of people. Right, so then some people randomly get chosen to see ad A, some randomly chosen to see ad B. And then you track, right? How many views do each of them have? And then, very importantly, how many clicks do each of them get? So what's the click-through rate for each? Okay. So this is what we'd have. So we have ad A. It was seen roughly 42,000 times and got 3,200 clicks. Meanwhile, ad B was seen roughly 37,000 times and got 4,500 clicks. So what we want to know is there a significant difference in the click-through rate for these two? Right, so we're going to use this as the basis for our template. So what we need then is a row for each of our samples. So we have that for A here and for B here. And then we need the first column is going to be our successes. So we're considering a click a success. And that makes sense because in a marketing context, we want you to click on the ad. Right, so a click is a success. The views here, that'd be our sample size. So you need successes and sample sizes as your columns, and then each sample 1, sample 2, as your rows. Now we're going to add some things to this table. So we're going to add first a proportion calculation. And that is just taking, again, successes divided by the sample size for each row. And that is the thing we're going to be comparing. So the question is, are these two, are they far enough apart that we can say that they are significantly different, statistically speaking? I'm going to add one more row as well, a total row, which is going to add together all of the clicks, so that is all the successes, and then also add together all of the views, that is the entire sample size. And then we'll calculate that proportion as well. We're going to be using that in one of the next steps. Now we need to start looking at the test material. Right? So we need first an alpha, that is our level of significance, which we choose. Right, we know 0.05 is typical, so I'm going to go ahead and put 0.05 in here for now. Next thing we need is a pooled standard error. Okay, let me widen my column A here to give us a little bit more space. because we're going to be putting some titles of things in here as well. So our pooled standard error, what this is going to do, to calculate the standard error when you're dealing with multiple samples can get kind of tricky. So what we're going to do is actually use our pooled data, that row number 4, so that the total row, to give us some of that information, but then we're also going to take into account the fact that it's not totally balanced. That is, we didn't have the same number of views or the same sample size for each of our two samples that are contributing to it. So here's how we do that. All right, so we're going to calculate the square root of pooled proportion times 1 minus that pooled proportion. This should feel somewhat familiar, similar to the previous template that we just did. Then we know before we divided that by the sample size. Now though, we're going to multiply by 1 divided by the first sample size plus 1 divided by the second sample size. So that is how we account for the fact that this is not coming from one big sample of 78,500, but rather two separate samples, one of which was a little bit bigger than the other. So there's our pooled standard error. The last thing I need is the z-statistic. For our z-statistic, that is, we will look at the difference in proportions. So we take d2 minus d3, that's the proportion from one sample, subtract off the proportion from the other, and then we divide by the pooled standard error. And enter. And there's my z-statistic. The last thing I need are those basic stats coming out of the hypothesis test. So let's go ahead and do that. So we need our z-critical for one-tailed test. Let me add that. This is going to be the absolute value of, again, we're going to invert the normal distribution. This will feel very familiar because it's basically the same formula we used before. So probability would be our alpha, mean of 0, standard deviation of 1, because it's the standard normal distribution that we're using. So standard normal distribution means mean 0, standard deviation 1. All right, so we use that formula there. Then we need the p-value if we're doing a one-tailed test. And our formula here, again, very similar to last time. So we're using the normal distribution, norm.dist. Our x value would be the negative absolute value of our z-statistic. And then again, 0 and 1 because it's standard normal, and true for cumulative. The next one would be our z-critical for two-tail, which is the one we actually want here. That's our absolute value, again, of the inverted normal. But now we take our alpha and we divide it by 2, because we're dividing that up over two tails, and 0 and 1. Good. And finally, we need the p-value for a two-tail test, which we can just take 2 times what it was for the one-tail test, and we're good to go. Right. So now we interpret this. Right. So again, for me, it's way easy for me to interpret the p-value. So I know my level of significance is 0.05. So as long as I'm more consistent than that, I'm good enough to say the null is true. My null hypothesis here is that the click-through rate is the same. Right? If you're testing for equality, the null hypothesis is always equality. Right? So in this case, null hypothesis, the two are the same as each other. Right? Our data is consistent enough with that hypothesis that that is the conclusion that I'd reach, that we can not reject that null hypothesis. We will go ahead and act as if it is true, that the proportion, in this case the click-through rate, is the same regardless which of these ads we got. So that would be how we do that. Now, I do want to give kind of one note before I leave, and that is some of how this is calculated and what that means for your interpretation. Right? So all of the one-tail stuff, whether it be based on our formulas or whether it be based on this output that we get from Excel itself, it assumes that you're not dumb. Right? By which I mean, it assumes that you go through and manually check your null hypothesis first. So let's say, we'll go back a little bit. We're here in task 3, where we were comparing those that did all the homework versus those that didn't. Suppose that my null hypothesis was that those that did all the homework would score at least as well as those that did not. So it's a one-tailed test now. Well, in this case, when I just look at the means in a glance, right, that's obviously true. Right? It is obviously consistent with the null hypothesis. But then when I look at the p-value for the one-tailed test, that's really, really low. That would suggest rejecting the null hypothesis. The reason for that is that this one-tailed test is calculated assuming, right, that the data is not consistent with the null hypothesis. So it's trying to figure out whether it's inconsistent enough for you to reject the thing. So if you're going to do a one-tailed test in Excel, highly, highly recommend, actually not just recommend, it is required, that you will check the mean values first. If they're consistent with the null, you don't reject it. It's only if they're not consistent with the null that you'd even bother to look at the one-tailed test. Right. So that's it for that. I hope this was helpful, and this is Profi signing off.